Hey everybody, this is your calculus video on section 2.2, limit of a function and limit laws. So there are several limit laws that we'll get to. There's several rules about it, and there's also some shortcuts. So your objectives are to be able to solve problems involving limits from graphs, existence of limits, calculating limits, using your limit rules, limits of average rates of change using the sandwich theorem, which is like trapping a value between two values, and estimating limits. So why we're studying this is limits are one of the main concepts in calculus courses. Sometimes the value is the same if you approach it from the left or right, but sometimes it's different or undefined. So a quick picture about that is, what if we just had something like a parabola, and so it's approaching the same value from the left and right. So that's where it's like continuous. Now sometimes you would have something like here and then it jumps up and here. So then you can actually see the value from the left is not the same as the right. So in that case, the limit does not exist. So that kind of jump discontinuity is one example of why a limit would not exist. So those are some of the things we're going to be talking about. So limits of function values. Sometimes we find ourselves interested in the function's behavior at a particular point, but not at C itself. So for example, if you're dividing by 0, but you can say, well, I know on the left and right it's approaching, then you could have a hole in the graph. So the informal definition is listed. Basically the limit of f of x as x approaches c is L, which is the formula limit x approaches c, f of x equal L, where L is the limit. Essentially the definition says that the values of f of x are close to the number L when x is close to c. So what you need to think of is x and c are related, and f of x and L are related. So the x and c would be the horizontal, and then the f of x and L would be the vertical. The value of the function at c itself is not considered, and our definition is informal because the phrases like arbitrarily close and sufficiently close are imprecise, meaning it depends on the context. Nevertheless, it is clear enough. It's pretty technical, but that's from the book. Okay, so there are two formulas that are pretty straightforward. One of them is the limit of a constant. So basically the limit of a constant is that constant. So for example, the limit of 3 is 3. Now if it's a limit of x, then the limit is the number you were replacing x with. The number you were replacing x with. So in words, the limit of x as x approaches c is c. Now it says to see example 4 on page 47. Example C. or example 4. So in this one, you have a piecewise function. I'm trying to make it where it's visible. It's right here. I don't think you can see that very clearly. No. Okay, let me just move this. Maybe this works. Okay, yeah, that's pretty decent. Okay, so on example 4, it says discuss the behavior, and there's basically a bunch of piecewise functions. One of them is just approaching numbers at different intervals in inequalities. This one's a rational function when it's not 0, but then 0 when it is 0. That's pretty typical in calculus where they fill in the hole. So then your domain would be all real numbers. And then they also have one where it's using 0 for the left and using sine of 1 over x for the right. So those graphs are right here. So on this one, it's like a jump or step function. On this one, it's a rational function, except for at the point. And on this one, it's the trig function on the right and the line at 0 at the left. Okay, now I'm going to put this back up. Okay, so you have a function that jumps, which is the unit step function, and it grows too large to have a limit, which means it's not bounded. And there's the third one, which it oscillates too much to have a limit. So those are ones with no limit, either jumping, going to infinity. Well, this one was negative infinity as x approaches 0 from the left, and it was infinity as x approaches 0 from the right. So they were different, and then this one was just oscillates too much. Okay, so now you have some of your limit laws. You have that the function approaches L, and the limit of g of x is going to be m. Okay, this will make more sense when we actually show the numbers. So for f of x, they're having L, excuse me, L, and for g of x, they're having m. And it tells you to find the limit of sum, a difference, and a product. Okay, so for the sum rule, what we're doing is we're just going to add L and M together, as you would probably expect. So in words, the limit of the sum is the sum of the limits. So for example, if the limit of this one was 3 and the limit of this one was 4, then sure enough, you get 7. Just as a random example. Now in the difference rule, it's the same thing, where the limit of the difference equals the difference of their limits. So in that example, you'd have to do 3 minus 4, which is negative 1. So then you have one that's called the constant multiple rule. And so if you have like a coefficient in front of a function, then you're going to have that constant times the limit. So that's the constant multiple rule, and you'll see an example. There's also the product rule where you're multiplying. So the limit of the product equals the product of the limits. Now, when you get into the quotient rule, it's a little bit trickier. You have to do the limit of the denominator first to see if it's even defined or not. And if the denominator is 0, the problem must be worked differently, like by factoring or doing the operation. In words, you're finding the limits of algebraic properties, and you may have to factor by grouping. That's when there's 4 terms. So the limit of the quotient does not equal the quotient of the limits. So that's the first one that's different. Then you have the power rule, which is also a little more complicated. So you're raising your function to the power, and then they're saying that's the same thing as L to the power. Then for the nth root, it must be defined and not imaginary. In other words, you can't have a square root of -16, since that's 4i. And if it's even, we assume that basically the y values are positive. You also have a root rule, where if you have the nth root, then you put it as L to the 1 over n exponent. And then you can extend those rules to any number of functions, not just 2 functions. So now we're going to talk about evaluating limits. So if you have a function that's like a polynomial with only 1 term, that's called a monomial. The limit of a monomial, if it's ax to the n, would be ac to the n. So you're basically substituting, putting c where x was. You'll have to find the limit of a polynomial, and if it's a function, then the limit of p of x is p of c for any number c. That's when it's easy. You just do it by substitution. In words, the limit as x approaches c, all we have to do is evaluate it at c, which is why I say substitute c for x. Then you're going to also have limits of rational functions, where you could have something like x plus 2 on top, x minus 3 on bottom. And then you're also going to have to eliminate common factors from 0 denominators, where it's no longer 0 at c. If that happens, we find it algebraically by substitution. And then you can also use calculators and computers, but the problem is sometimes they give you rounding errors. But in general, if you're being asked about x approaching 3, then you could try substituting 2.999 and 3.001 and see if it's the same answer. So even if it's undefined at 3 itself, this is basically like this problem. It'd be undefined at 3 itself, but the limit would exist because the left and the right would approach the same answer. Then we also have a little bit on finding the average rate of change, which was your change in y over change in x, or f of b minus f of a over b minus a. And then the sandwich or squeeze theorem is if you know the limit of the left and you know the limit of the right, then if they're the same number, then it can be assumed that that limit is the same thing. Again, we'll show an example, but this is the definition from the book. And then to find limits, use the graph. Okay, this is the most important part. Use the graph, substitute using c, substitute values close to C or factor first and then substitute. And be careful on your true-false questions, making sure you look at both sides of C. Okay, so let's get started on the problems. So again, what's nice about this is you have a graph right there that you don't have to draw. You can just point it out. So if you're doing the limit as x approaches -6, -6 is right there. The limit is 0 since it approaches -6, 0. Now, sometimes they're going to say, does f of -6 exist? And that would end up being false or no, because it's not part of the graph. So just because the limit exists doesn't mean the function exists. So now they're asking about -1, and at -1 it's this, which is -4. And it's -4 from the left and the right. Just like this other one, from the left and the right. Now, at 0, what's happening? So at the actual y-axis, you have one function that's up here, one that's down here. So they're not approaching the same thing from the left and the right. So that's when the limit does not exist, since it's not the same from the left and the right. And then what is the limit when it's -0.8? So that's a number between -1 and 0. So that limit would be -4. So that's from the horizontal line. Y equal -4. Okay, so that's how you do the first one. Okay, on our next one, we have a graph. And it looks like a V graph, kind of like an absolute value, but it's not. It's probably just piecewise. So the statement that the limit exists as x approaches 0, that's true. By the way, your answers are here, and you can see all your trues and falses are bold, but sometimes it put it in a different order. So be careful, and you may want to label it to the side. So when it approaches 0, it does exist. And then they say, does it equal -1? No, it doesn't. Just because the point is doesn't mean the limit is. And then does it equal -2? Yes, that's true, because it's the same from the left and right. Now we're going to talk about 2. So those three kind of go together, because that was all about 0. Now on this one it says the statement with x approaching 2, the limit is -2. That would be false, because only from the right. And on E, by the way, if you want to number these also, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. That may help you when you're referring to your answers. So on number 5 with E, because E is 5, the statement that the limit is 0 is also false. The reason is because it's only from the left. And you have to have something exist from when it approaches the same number from both the left and the right. So now for number 6, the limit exists at every point within this open interval from -3 to +2. That's true. On number 7, the limit does not exist at 2 is true because it was different points. Since different points on the left and the right. Okay, now you have some function parts about is the value -1 or -2 when x is 0. So when x is 0, it's -1. And so 8 would be true, which means 9 would be false. So it's actually talking about the point, not the limit. And on this one, they're talking about when x is 2, and the value is actually -2 because at 2, 0, it's false because it's a whole at 2, 0. So again, that would be false, and then 11 would be true because we're talking about 2, -2. Okay, so that's kind of lengthy, but at least you have a really good description, and I am glad that you're able to see the paper with it instead of having to write down all your examples. Okay, so you can just mark on this sheet. Let's do a couple more. I'm not sure how much time I have for this, but we'll see how far we can get. Explain why the limit of this one does not exist. So if we're doing a graph, now first off, we would just graph the function to be x over absolute value of x. Don't try typing in limit. We just want x divided by, remember that's the absolute value symbol, so you have to do the button to the right of the 9 and then right over there. So remember this is the button to the right of the 9. So what we have is a type of step function where it has a jump discontinuity. So as x approaches 0 from the left, the function approaches -1, and as it approaches from the right, it's 1. So you can see that on the graph. It's like this and like that. And we want to know why the limit doesn't exist. And out of these two choices, it's not because it's not defined, it's that the number is not the same. There's not a single number. So in other words, it's different on the left and right limits. Okay. Now on this one, we want to find the limit, and basically on a problem like this, you probably just want to try substituting. And so you're going to do 16 times -1/4 and then have 3 times negative 1/4 plus 16 squared. And let's see what we get. So we go to the calculate screen, and we're going to do 16 times negative 1/4 times 3 times negative 1/4 plus 16 squared. And so you can see that gives us the exact answer. So all we had to do is plug it in. So that would always be your first step, like try to substitute. Now, if you end up with a 0 divided by 0, you have to do it a different way. On this one, we're going to put 5 over the square root 5 times 0 plus 1 plus 1. Make sure y'all pay really close attention to where the square root ends, because this plus 1 is in the denominator, but it's not under the square root. Now, sometimes, like in this one, you shouldn't even use your calculator, because you know 5 times 0 is 0, and so you would end up with the square root of 1 plus 1. So that's just 5 over 1 plus 1, which is 5/2. So that one's kind of easier to do without a calculator. Sometimes it works out that way if you have a 0 that you're trying to plug in. Okay, on this one, it looks like you can also just plug in. I think. No. Look at the bottom. Look at the denominator. I would have 5 squared minus 25, which is 0. So that's a divide by 0 situation. And so because of that, you can't substitute. You have to do some work first. And so what we're going to do in this problem is our step 1 would be factor. So if we have negative 40, there's a few different ways to get it. 1 and 40, 2 and 20, 4 and 10, and 5 and 8. Well, we want the one with 5 and 8 because we're trying to get 3. And since the 3 is positive, I need the 5 to be negative. So that means this factor, I'm going to use x instead of t. I'm going to have x minus 5, and I'm going to have x minus 8. I'm sorry, plus 8. So that's my numerator. And then on this one, it's x squared minus 25. So that's like the difference of two squares. So you need x minus 5, x plus 5. Now, remember, if y'all actually have to type a variable in Math Excel, to use that variable like t. But when I'm just working my math, I prefer x. Okay, so notice this cancels because it's really a hole in the graph at 5. And so if it cancels, then try substituting here where you'd say 5 plus 8 over 5 plus 5. So that's 13/10. So that's your answer. And then you have a few like that where you have to do something, not just plug in. Because on this one, if you did in your denominator the square root of 39 plus 10 minus 7, well, that'd be the square root of 49 minus 7. 7 minus 7 is 0. So you have to do something different on this problem. Now on this one, it might be easier if we graph it, because I don't really feel like doing any rational part of it. Um, so let's try graphing x minus 39 divided by parentheses the square root of x plus 10 and then minus 7. Okay, so that didn't show up, but we want when x is approaching 39. So we can move our window out. I'm going to move it to 60. Okay, that didn't really help. Now I'm going to do menu 4A, and now it does. So I needed to set my x max equal to 60. Then I needed to do menu 4A, which is zoom fit. Okay, so now what's actually happening at 39? It must be a hole in the graph, which is what we kind of thought. So if you go in your table, you could just hold this down until you get there, but that's kind of wasting time. So you want to go to your table settings. You first press menu, then you press 2 for table, then 5 for settings. And we just want to start our table like right around there. And we're still counting by ones. And notice that it's undefined right there. But on 38, it's 13.9, and on 40, it's 14.0. So that's actually going to be my work. So at 38, it's 13.93. At 39, it's undefined. And at 40, it's 14.07. So this is actually the first time you see the sandwich theorem. So you can say on the left side, it approaches 14. On the right side, it approaches 14. And so then 14 is your answer. Because there's not a huge difference. It's really approaching 14. And you're going to do the same thing here. So here we could try negative 19, and negative 20 would be undefined, and try negative 21. See if it matches the same number. Now, if we wanted to be more precise, we could have tried negative 19.999 and negative 21.001. So that would actually be more accurate. But if you're doing that, then you can't look in your table. And I feel like being more efficient, so I'm just going to use this part. So we're saying our function is 19 minus the square root x squared minus 39. All of that divide by parentheses x plus 20. So here we do have quite a gap, but what we're interested in is at the negative 20. So you can either jump in your table or just hold this down. So at 19, or negative 19, I get 1.0556. And at 20, it's undefined. And at 21, it's positive 1. Oh, both of these are positive. It's positive 1.0499. So this one doesn't give me an exact number. So let's just say, what is 1.05 as a fraction? That's 21 over 20. So that was not what we wanted. Okay, so let's see. What if we tried something more accurate? Let's try that. Okay, so because what I'm thinking now is, what if we needed something like 1.0 and a bunch of 5s? And that's 19/18. Whoops. Okay, so those are two like swing and miss. I'm going to pause this and get back to y'all.